A useful tool for drawing some molecules such as sugars is the Fischer projection. A Fischer projection is used for drawing chiral centers quickly. In this case, the horizontal lines are going to be wedges. We could draw that in here like this. And any of the vertical lines are going to be dashed, or they're going to be pointed away from you. How can you tell the stereochemistry for this? Well, one way we could do that is first, if we rotate it 90 degrees this way, our ethyl group will be pointed still as a wedge, or a dash. The methyl group will be pointed as a dash. The hydrogen will move down, it's still a wedge. And the hydroxyl group will be pointed up, it's also a wedge. Now if we take this and we rotate it towards you along that axis, basically we're pushing the hydrogen up, we get a similar shape to what we're used to seeing, where we have the ethyl group here, the methyl group down here, the hydrogen, because it swung up towards you, is here, and the hydroxyl group ended up swinging backwards, so it will be back here. You can now assign the stereochemistry relatively easily. Assign the priorities, 1, 2, 3. This is clockwise, but the hydrogen is pointed in the wrong direction, so this will be S. A quick way to figure this out if we have a Fischer projection is we look at the lowest priority on the Fischer projection. It's this hydrogen. Notice it's pointed towards you. So whatever stereochemistry we find, it's going to be the opposite. So let's assign the priorities, 1, 2, 3. These are going clockwise, which would be R, but again, the hydrogen's going the wrong way, so we can quickly assign this as S. Take a look at this example, where the hydrogen is now on a vertical line. Again, we can draw our vertical lines as dashes, and the horizontal lines as wedges. We can assign the priorities, 1, 2, 3 in this case. Again, we're still going clockwise, but in this case the hydrogen is going back, it's going away from you, which is what we would like in a normal stereochemical assignment, so this will be R. A lot of times it's a lot easier. The whole purpose of a Fischer projection is to compare two different stereoisomers, or two different molecules. So if we look at these first two, notice the bromines on the right switch to the left side. These are mirror images of each other. We can draw a mirror image right down here. We can easily tell that these two molecules are enantiomers. In the other example, only one of the bromines switched, that would be this one, compared to here. So these two, only one stereocenter changed of the two. These two molecules are called diastereomers. Another way that Fischer projections are used are if we're comparing molecules that have somehow changed. Notice the methyl group here on the top is on the bottom in all of these three examples. This molecule actually matches one of the others. You can't simply just flip the molecule over. You have to rotate it in the plane of the paper. Think about it this way. If these horizontal lines are wedges and we just flip it over, they're going to be pointed down. They're going to be dashes at this point, which is going to change the stereochemistry. So we have to keep that pointed up the whole time. So if we want to compare this molecule to any of the others, what we have to do is rotate it all the way around in the plane of the screen and redraw it. The methyl group went all the way around, it's on the bottom. The ethyl group went all the way around, it's on the top. The bromines went all the way around. They're going to be on the left, and the hydrogens will be on the right. So if we're trying to match up this molecule with one of the other molecules, we can say that these two will be the same.